All right, let's prove this theorem now. So first let's remember what this theorem says. I'm doing rook theory. I'm interested in non-attacking rook configurations. This is an example of non-attacking rooks because every rook is the only one in its row and in its column, okay? I'm interested in this board B that I have. So I've got some fixed board, B, which is a subset of the full chessboard that I have. And I'm interested in how many rooks live on that board. So this number R sub k, remember that is the way to place k rooks, non-attacking, onto B. So an example, if this rook's not here, so now we have just these 3 rooks are all touching the board B. I don't know if you can see the board B. I'll try to move them so you can kind of see. These are on the board B. So this would contribute at least 1 to the number R sub 3, okay? This rook here doesn't count, but it is going to contribute to our other side, which this guy, remember that the definition here is this is the sum from j equals 0 to n of nj x to the j, where remember that nj equals the number of ways we're going to place n rooks onto the whole chessboard, and we're going to hit B j times. Okay, so that's what we're trying to prove, is that this formula holds. So let's give a combinatorial proof of this fact. That's always the most satisfying proof. And what I'm going to do is I'm going to think of x instead of as a formal parameter. I'm going to think of it as a positive integer. And that's completely legitimate to do, because if I can prove this is valid for every positive integer x, then that proves that this polynomial identity has to be true, because it is a polynomial. It has finite degrees, so if it's true for infinitely many values, it's true in general. So that's our strategy. We're going to regard x as a positive integer. Okay, and now I'm going to interpret the left-hand side with that in mind. So what's the left-hand side? How can we think of this? Place in rooks onto the chessboard, the full thing, okay, and we're going to label the hits on B by some positive integer from 1 to x. That's exactly what this is doing. If we hit it j times, we get j choices for x. So that's going to be x to the j choices for labels when we hit B j times. Okay, that tells us what the left-hand side is. That's a combinatorial interpretation of this left-hand side where we're thinking of x as some integer. So in this configuration that's about to disappear, sorry for this, I could label this guy, if x is 12, I could label this guy with 11, 6, 9, no label here. Okay? So that's what the left-hand side is saying. That's how we get this x coming into play. So let's move our chess pieces and delete our board so that we can continue with the proof. I need to show how the right-hand side counts the same thing, but of course we're going to count it in a different way. But that's what I'm going for. I'm thinking of it as the chess pieces that hit B. So anything that hits B is going to get a label, and anything that doesn't hit B doesn't get a label. And the labels come from numbers 1 up to x. X is a number in this paradigm. So think about it this way. What's RK? So I'm going to place K rooks onto B. Okay, that's the first thing that I'm going to do, and that's giving me my number R sub K. Okay, there are R sub K. See, there's not quite enough way to see that. So there's R sub K ways to do that. That takes care of this. Now I'm going to take care of this, x minus 1. So I get 1 fewer label. Fine. We're going to label those from x minus 1. So these are our labels. So we get to label them 1, 2, 3, all the way up to x minus 1. That's going to give us k choices of x minus 1, right? So we choose numbers 1 up to x minus 1, and we do it k times. What's this permuting thing doing, this n minus k? Well, if we think about delete the row and column for each rook. If we think about doing that, that's going to give me what? An n minus k board. N minus k by n minus k board. So we're going to place n minus k rooks anywhere we want. I'm now ignoring b. And this is going to give me any permutation. So what I'm doing is if I think of it like this, and I had my red cell here, and that's where my rook was, then what I would say is, okay, let's just zap that out of existence for now. That's where my one rook goes with my label. And now I'm just looking at this 2 by 2 board, and I'm going to get 2 factorial ways to put anything I want on that. And I no longer care about the board B. Okay, but how do I recover that? Because there's going to be some repetition. Well, I only used x minus 1 of my numbers, so I have a number left. So what we're going to do is, among these, label the rooks on B by n. Now this is an invertible process, right? So if I just do this, if I had some cell over here, I kind of ignore that would be a part of B. But now what I'm doing is I'm remembering that because I have one label left, and that label is going to go on those. And then you can see how this bijection works, right? If I have any configuration that satisfies this, then what I can do is all the guys that are labeled by oh, I said n. Sorry, that should be x, the biggest label. So any of the guys that I have over here that are labeled by x, I can think of just plucking those guys off the board, and anything that's not on B, pluck it off the board, and now I have RK. I have my rook number. So this gives us a bijection between these two sets. We can think of it this way. So that gives us our combinatorial proof of this identity. And again, specializing, the really interesting thing that we can do here is if we specialize at x equals 0, so what is n of 0? Well, in this paradigm, right, I'm setting x to 0, so everything dies except for the constant term here. So this is going to equal n sub 0. Only that guy, the constant term, survives, but over here it's a little more exciting because I have this x minus 1. So this is the sum from k equals 0 to n of minus 1 to the k, that's coming from here, the rook number times n minus k factorial. So that's why we're getting this interesting analog of the derangement problem. That's why we're getting this nice generalization of it. And in fact, if we just take a moment to go back and look, what happens if we take our board to be the diagonal board? If we take our board, N0 says you want to hit the board 0 times. So N0 says never hit this board, never have a fixed point for your permutation. So what does that mean? That means that the number of derangements of n is equal to this n sub 0 for this diagonal board, and that is equal to the sum from k equals 0 to n of minus 1 to the k. How many ways can I place k non-attacking rooks on this board? Well, however many rooks I have, just pick which cell's on the diagonal. It's automatically going to be non-attacking, right? So all you're doing is choosing the cells. So the rook number in this particular case is super nice. It's n choose k, n minus k factorial. That's exactly the derangement number that we had before. So this gives us a really nice way to generalize derangements, and now we have this nice combinatorial proof of it as well. So in this special case, we're getting a direct combinatorial proof of the derangement number.